make it physically rather the same everywhere, but compositionally there are major differences. The second step in formation is the impact environment. Impacts are the dominant geological process on the moon. So the larger impacts break up that crustal material, create new regolith, blowing it out. It also so there is lateral mixing. Anywhere you go on the moon, if you scoop up a handful of regolith, you will find soil grains from every part of the moon. So there are highland grains in the Maria, there are mare grains in the highland, but it's not complete mixing, so they retain their regional characteristics. Then there's bombardment all the way down to dust grain sizes. So the micrometeorites are churning the surface of the moon. About every 80,000 years, the entire surface of the moon is flipped over to about a centimeter deep. This causes rocks to slowly melt away, become fine. The finer soil becomes even finer, and it creates a lot of glass. On impact, the impactors vaporize, and a large part of the target material is melted. Some of the impactor results in contact jetting, which is molten material. And this flown out molten material quickly quenches, it doesn't recrystallize, so it becomes glass. And as a result, the lunar regolith is a very complex assortment of grains. You can find fragments in the center picture, fragments of rocks of different types, fragments of pure mineral. You can also find glass beads. That you can see the two spherical glass beads in that picture. Those are glass. There's a glass bead on the left side. You can see that glass bead has two impact craters on its surface from very, very tiny impactors coming down from space. And then on the right, you can see a picture of an agglutinate. This is a splatter of glass that bonded together other soil, other lithic and mineral fragments, but the substrate of it is glass. Now, one of the questions is, what about metal from metal meteorites? I'm going to address that in a minute. Where does the metal in the lunar soil come from? But if you look at the soil, it's a mixture of rock fragments, glass, breccias, agglutinates. There's really not a lot of free metal. There is some. The minerals include the feldspathic, calcium aluminum stuff, the basaltic, iron-bearing stuff, ilmenite, which has titanium and iron. And there's a lot of interest in sorting this. Can you put it into a machine which sorts the different minerals so that you have the iron-bearing ones, the ones that you can easily extract the aluminum, separated from the rest? One last thing I need to mention on the impact environment is that these micrometeorites are constantly vaporizing material, and that vapor deposits all over the surfaces of the grains. And so there's this glass coating on the sand grains. And inside that glass coating, the metal condenses into little tiny particles that are like 30 to 100 or 300 atoms wide. We call nanophase iron. And this is 40% of the free metal in the soil is actually in these nanophase iron. It's not free physically, it's reduced metal, not oxidized. And this causes the dust to have highly magnetic properties, which make it difficult to beneficiate the soil. And I'm going to mention that in a minute. Okay. The other major material resource, are the volatiles. It's been hypothesized for a long time that the moon contains volatiles because, by definition, a volatile is something that flees from energy. And so it's amazing we have volatiles in the inner solar system at all, that Earth has an ocean. And the reason we do is because the solar system was disrupted and the icy bodies a lot of them were sent inward, which bombarded the inner solar system. The late heavy bombardment delivered a lot of the water and the carbon that we're made out of. Well, the moon has cold spots as well, and so some of these volatiles were sequestered in those cold places. The left shows a illumination map averaged over a day. This is at the south over a year. This is the south pole of the moon. The dark areas never get sunlight at all during an entire year. But even in the shadowy areas, it's very cool. So the right is a model that shows where ice would be stable, how deep under the surface. The white areas, ice is stable right at the surface. The very red areas, you only have to go down a couple centimeters to get where ice is stable. So even outside the permanently shadowed regions, in the shadowy areas where there is sunlight available, you can get ice in the polar regions. At least it was hypothesized. When we put spacecraft in orbit around the moon to get neutron spectrometry data, the spectra of the neutron velocities indicate that there's a lot of hydrogen at the poles of the moon. We didn't know if it was water or if it was just free hydrogen or hydroxyl. It could have been just hydrogen that collected from the solar wind for all we knew. But then the LRO spacecraft is able to look at the hydrogen bands that come from the clouds in deep space that are reflected out of those dark craters on the moon, and it indicates the existence of a frost or a very fluffy surface material in those craters. It's been hypothesized that it's water frost. And then also the radar on the LRO, the radar cross-circular polarization ratio shows the existence of blocky material inside some of the same craters that have the neutron spectra evidence of hydrogen. And usually blocky material is found on the outside of craters, not on the inside. And so those blocks have been hypothesized as chunks of ice the size of your fist. The best evidence comes from the L-Cross impact. In 2009, NASA crashed the L-Cross spacecraft into Cabeus crater, and 2 spacecraft watched the ejecta fly out, and the ejecta was analyzed, and we see that it's about 5 weight% water, 5 relative to the soil, and then about 4.5 weight% was a lot of other volatiles, including sulfides, carbon compounds like methane, ammonia, so there is nitrogen available on the moon. And so the nitrogen and carbon and hydrogen that we used to think were largely absent on the moon are in abundance in these deposits. Also on the right, there's a dip in the spectrum in the 1.7 to 1.8 micron band. And that dip indicates that it's actually crystalline ice. It's not amorphous. So this is crystallized ice crystals that were blown out by the ejecta blanket. So all the evidence goes together to fit a model, and I believe this model is correct. Dana Hurley at Johns Hopkins University and her coworkers have modeled during the late heavy bombardment, ice sheets would have formed in the permanently shadowed regions from asteroids and comets hitting the moon. Those ice sheets froze, and they were and it became another type of bedrock. Because at those temperatures, ice behaves like granite. And so it's just another type of rock that gets beat up by the impacts on the moon. And so the ice grains are just another type of mineral mixed in with all the other minerals in these areas. And so it's apparently granular crystalline ice, like grains of sand, all the way up to rock sizes inside these areas. There are other volatiles on the moon. There's globally a veneer of hydrogen from the solar wind. It's very low density, like 65 parts per million in the equator, and it's just a very thin layer. So it's probably not a resource you could use. But there are volcanic glass deposits that have about 50 parts per million of water in the bulk of those deposits at other locations around the moon. Okay, so where do we get metal? What about asteroids? If the asteroids vaporize, and by the way, I've been in arguments where the planetary scientists and the geologists argue against the mining engineers that there are no metal asteroids on the moon because they vaporize. And so, well, there's contact jetting on impact, so some of the molten material will squirt out. But where does the metal on the moon come from if it vaporizes? Does it vaporize or not? Well, there have been studies of the composition of the soil, comparing it to the composition of rocks. And there is definitely a compositional difference. And when you look at all the elements that are enriched in the soil, you can say what type of asteroid do they match. They don't match M-type asteroids, okay? So there's not a significant signal of metallic asteroids in the lunar regolith. It is carbonaceous. So the material on the moon that has been bombarding it largely is carbonaceous material. In fact, we can say it's C1, which matches the Tagish Lake meteorite. There is metal in that, but there's a lot of other stuff too. Now, this is a C1 meteorite. This is the composition of it. There's olivine, there are sulfides, iron sulfides, there are iron oxides, which are good because it's easy to get the oxygen out to get the pure iron. Those would be an ore on the Earth. And there's a lot of clay. But you don't find any clay in the lunar soil, and that's because they vaporize on impact. And by the way, the sum, that 2 weight percent, if you add it up, that equals the total flux of material raining down on the moon. So that 2% does add up to the entire inventory that we would expect to be there. So where does the metal come from? There is about 0.5 weight percent of free metal in the soil of the moon. But when we say free, we don't mean it's all physically free. About 40% of that is inclusions that are the 30 to 300 atoms wide, little tiny particles. And when you read the literature, they call them particles, and it might be confusing. You might think that those are sand particles. They're not. They're little particles of iron embedded in the glass on the surface of the dust grains. But there are free metal particles that are sand grain sized. And when you study the composition, only about 15% of them came from meteorites, probably from chondrites, which are those clay meteorites. The other 80% of the metal came from the lunar rock itself. Well, how did metal get in M-type asteroids in the first place? It got there by the heat and the pressure creating the metal. Well, every time there's an impact on the moon, the heat and the pressure reduces the minerals and creates metal in the soil. Okay, I've blown through a lot of my time, so I have to be fast. I'm sorry. So there are methods to beneficiate using magnetism and density differences and particle size differences. And there have been some studies. Larry Taylor says it doesn't work, but other researchers have found ways to make it work. There needs to be more work beneficiating metal from the soil. The ores on the moon. Are there ore bodies? What about around impact craters? We find ore bodies on the Earth around impact craters, but those were formed not from the asteroid material, but from the native Earth minerals that were processed by the heat of the asteroid in the presence of water. The moon doesn't have water, so we don't know if there are going to be ore bodies around the impact craters on the moon. But we do know there's abundant anorthite, which is good for making aluminum. Throughout the highlands, the moon's surface is basically made of aluminum ore. And it's used on the Earth for making aluminum. It takes twice the energy of bauxite, but twice the cost is really cheap on the moon because 99.98% of the cost is transportation. 0.02% is making the aluminum. So if you double the cost of making the aluminum and eliminate 99.98% of the cost, that's amazingly cheap. So we can use anorthite and make aluminum. It's all over the moon. Ilmenite for iron. It does bubble up, and there are deposits of ilmenite. We have developed methods for making ilmenite, but they haven't. We know about the methods, but they haven't been built yet. We have built methods of working with ilmenite to get oxygen. We've tested them on Mauna Kea, and they work. We've also tested more advanced methods using methane as a reactant. We've tested those on a volcano in Mauna Kea, and they work. And notice the size of the equipment is not gigantic. This is a refrigerator-sized unit that's processing the ilmenite, doing the metallurgy. So we can build equipment to go to the moon and make aluminum out of the anorthite, make iron and titanium out of the ilmenite. What about just basic regolith, which is everywhere on the moon? The bulk chemistry includes a lot of silicon, iron, calcium, aluminum, and magnesium. So if you turn that into metal, you will get what we call a mongrel alloy. Laurent Sabile at the Kennedy Space Center came up with that term. The best method is molten regolith. Well, one of the best methods is molten regolith electrolysis. You melt it, you run an electric current through it, you get two materials out. One is all the unreduced, the oxides, which you can use to make ceramics. The other is the mongrel alloy. Sam Schreiner at MIT did this for his dissertation. He did physics-based modeling of it, and he showed at different temperatures you can get different mongrel alloys, which are irons, silicon alloys that also include aluminum and titanium and stuff. He's done detailed modeling to show that it only takes 5 times more energy than making aluminum on the Earth. 5 times would be uneconomic to compete here on the Earth, but 5 times the cost of making metal on the moon versus making it on the Earth is incredibly cheap compared to transportation costs. Incredibly cheap. This will be vastly cheaper than transporting metal to the moon. So people have also developed methods called fluorine processing, sodium hydroxide processing. Another promising area of research is ionic liquids. These you can not only make mongrel alloys, but you can separate the metals out and make whatever metals you want. I've done a systems analysis of this about in 2012 with some coworkers. We estimated the mass of the hardware to do a complete supply chain on the moon. This was based on hardware that had already been built. We looked at the mass of equipment, the power requirements, the feedstock input, and the product output rates based on hardware that had already been built, extrapolating towards the more advanced hardware. When you do a system study, it shows that this hardware can this is not Earth independent. This is with supplies coming from Earth, but working towards Earth independence. And during that time, it can grow exponentially, and it gets all of its energy from the solar cells that it makes on the moon. That solar cells were based on Alex Ignatieff's work. And because there's a lot of uncertainty, I put a factor of 30 uncertainty in this. I said every generation, the hardware builds 30 times more solar cells than they actually need. Even with a factor of 30 conservatism, it was able to reproduce on a very fast metabolic rate. It could reproduce its own mass within 2 years, or 1 year actually. And this is with a factor of 30 uncertainty. So this would be economically viable on the moon. So you can make metals, you can do economic activities cheaper than transportation, and therefore I would say these are ore bodies. For the sake of time, you can read the conclusions, and I have a few minutes for questions. Yes?
This is more a comment than a question about meteorite impacts. There's a famous meteorite impact at a crater called Meteor Crater in Arizona. And there was extensive attempts to mine what was thought to be the meteor ore body at the bottom. Never found anything. But if your tour guide at Meteor Crater takes a magnet and just drags it through the soil on the top of the rim, there are metal fragments that just whiskers on the magnet.
Let me answer that, and thank you for bringing that up. For the sake of time, I skipped over a lot of this. So some of the differences are Earth has an atmosphere, which causes a lot of the burning off to occur at high altitude. And so large bodies survive some of the burning, but then because of the thermal gradients it creates in the impactor, it causes airburst, which decelerates a significant fraction of the material. Also, it fractions it into smaller particles, which would not have survived the early entry in small form, but it makes them small after entry. And because they're changed in ballistic coefficient, they can then slow down to a terminal velocity, which is sub-hypervelocity. And so things do survive on the Earth and on Mars. But also there are details. When we say there's not a significant metal signal in the lunar soil, that doesn't mean none survived. It just means we don't see it widespread above the signal level. So contact jetting and other things do cause material to survive even on the moon. And it may be, with more exploration, we can find ore bodies. There's a lot we don't know yet. There was a paper in 2012 in Nature, which said 25% of metal asteroids should have survived, fragments should have survived on the moon. People dispute that and argue about it, but more exploration will show.
Molecules had to go somewhere.
Yeah. Thank you for bringing that up. Yes?
If we posit a polar base of the moon, how far would one have to go to find acceptable deposits of all the different varieties of minerals one would need?
Okay, great question. So ideally, you would find a place that has ilmenite and anorthite and volatiles. And I'm not sure if that place exists. You would want to be on the edge of the mare and the highlands so that you get a lot of anorthite and a lot of ilmenite. But those places are typically far from where the volatiles are. However, South Polacan Basin is a deep impact basin that goes into the high iron minerals. So maybe somewhere on the edges of the South Polacan Basin near the South Pole of the Moon, you could find great spots for that. However, on the other hand, there's ilmenite and there's anorthite everywhere you go on the moon, just in lower concentrations. So with beneficiation, you could concentrate those at very low energy. So I think basically the answer is you could go anywhere on the moon that there's volatiles. So the polar regions would all work. Sure. Okay. All right. Thank you so much.
Okay, so continuing on with the next presentation. So an Earth independent colony needs parts, right, to be reproduced. And so our next speaker is going to be addressing that, Ryan Motley. He is with Wet Spark Innovations, LLC, and he's a managing partner with that company. It's located in Newport News. I always thought that was a sort of a cool name for a town. in Virginia, and his company develops and works with new materials and biotech. He is also a drone operator. In fact, I think, Ryan, don't you have a YouTube video, right, of that? And he studied biology, and he's also taking classes in aerodynamics and astrophysics. Now, relevant to this presentation is that he regularly works as a blacksmith and a machinist, and so he has sort of broad practical knowledge of this field. So he's going to be presenting about how will we produce parts from local materials. Welcome.
Morning, everybody. Are we all getting hungry yet? I'll keep it quick. A big asterisk for my presentation. I taught 7th grade life science for a year, and I now teach high school a couple days a week, just helping out. And I absolutely hate PowerPoints, and I hate just talking. I love interaction, so I'm going to try and cut through all my baseline info and get to questions as quickly as possible. And get to my presentation, actually. Doug. No problem. Oh, gotcha. Oh, it is touchscreen.
Yeah. Well, if it
We're
works.
having one of those. We're okay.
F5.
And we're up.
There you go.
Thanks. All right. So our very, very first question for the day is sort of why manufacture on the moon? It might be obvious because launch costs are absolutely ridiculous, but if we've got local resources, it's just easier to get stuff there. But we've got some benefits. A previous speaker talked about vacuum being a resource. The highest quality steel you can produce is produced in vacuum. So vacuum casting, you don't get any bubbles, you don't get any oxides, and if you want to roll that stuff out into hot rolled steel on Earth, you'd then have to clean off the scale before you got a clean billet of material. In space, that just doesn't really happen. The most you need is basically a garden shed to keep dust out, and you can produce all the clean iron that you want. As an engineering approach, however, we want to sort of take a look at the actual end products that we need rather than just say, oh, we're going to set up manufacturing on the moon and then go about it. I learned that the hard way about 5 years ago with a contract that we took on to develop a drone for someone. And like 3 months later, we decided that they didn't want the kind of drone that we could produce. And that was a huge waste. But on the moon, we're talking about some economic factors, social factors as we grow the colony, and just something to keep in mind. Virginia originally at one point was going to be a silk colony. We see how well that worked out. Things change, and we wound up producing a whole lot of timber. So look at the natural resources, look at what we've got, but look at what we actually need and can produce in an economically viable fashion, and things might change. On that note, I've had to pare down manufacturing as a topic. I mean, it's mind-boggling the different ways and things that we make. I mean, you've got everything, just reducing it down to metal, you've got everything from a jeweler that produces one really cool, pretty piece of material weighing grams in a month, all the way up to chip manufacturers that make millions of units in the same period. So it's a really broad topic spanning sort of different economies of scale. So we need to keep that in mind as we grow this colony, how that's going to change over time. Let's get to it. One other reason for manufacturing locally is I don't have to worry about the shape or size of the container that I don't have to ship something in if it's already there. This is actually a buddy of mine's trailer, Polydrops. If you're looking for a little RV type trailer, check them out. They're really cool. But if you're going camping and you need to take your habitat with you, it needs to fit in or behind your vehicle. If you're going to build the habitat there, you don't care. And then down below, we've got the Bigelow inflatable habitat module that's on the ISS right now. Even an inflatable module that collapses down and doesn't have to support launch loads, like a trailer, just like a module, a rigid module that's launched on a rocket, has to support those transportation loads. On the moon, we've got significantly lower gravity than Earth, but we also never see 3 times that on a launch if we never have to launch it. So we can build essentially weaker, but we can build to suit the use case rather than the transportation case, which almost invariably is better if you actually know what you're doing. So back to the engineering case. In terms of what we actually need to produce, that should drive the manufacturing methods. By the same token, however, if all of you were engineers and I asked you how to make a widget, I would get different answers based on your specific fields of study and what you're comfortable with working. I'm really comfortable with working with iron and a hammer and some fire, so I really want a gas forge on the moon, but that's not really practical because every like 5 minutes that I run that forge is going to be something like $10,000 worth of fuel just because we had to transport it from Earth. So don't ask me for a knife when we get to the moon. So basically, to steal Doug's image from earlier, we're going to need replacement parts for the stuff that we do launch. We're going to need equipment, hopefully telerobots. Telerobots and 3D printing, just like the engineering case where you want to look at your end product rather than the process first. No single technology is going to be our magic bullet. We've got literally centuries, millennia of steel production that should inform how we're going to go about things. But a few boots on the ground can be really, really useful for catching snags. But most of all, we're going to need structures. And this, I think, is where we're going to have the most benefit, at least with steel production, on the moon, simply because you can't launch but so big of a thing, even if it's really lightweight. So, on the far right there, we've got a standard 6-DOF arm from Fanuc. These guys are relatively easily shipped. They fold down compact. We should probably wind up shipping a few of these to begin with. But the parts that they're made of are largely low precision items that a lot of high precision stuff is bolted to. So if we can reduce that mass by about, I don't know, 80 or 90%, depending on the size of the arm, and just ship the drive motors and electronics, we could locally 3D print or cast all of those big bulky parts and not, again, have to worry about launch costs. The key thing about reducing costs for tools that are immediately useful in producing an economically viable product is it's a leverage item. So even if it costs a lot, if we can make sure that it lasts a long time, it will recover its own value. Things like life support systems don't in themselves have an economic return, but we need them or we die. So it's just sort of a bottom line cost. If we can produce small parts that are precision up there, then we don't have to ship any of that for replacement parts. And we're talking about everything from screws to gears to pressure vessels that will wind up wearing out. And 3D printing can do that, but we also will need some specialized machinery. Which brings us to the specialized machinery. There's really only 4 things that you can do to a piece of metal to turn it into a finished product. One is heating and cooling. So if I've got a piece of steel, regardless of the alloy composition, there's going to be some critical temperatures that you bring it up to or down from in order to achieve certain physical properties. As a blacksmith working with carbon steel, it's really simple. I've got iron and carbon, and there's a couple of temperatures where the phases change of the material, not from solid to liquid, but just the arrangement of the molecules inside, ratio of carbon and iron in each grain. If I take it above critical and just dunk it in a bucket of water and cool it rapidly, then I have probably the hardest material that I can get with that particular alloy of steel. So hard, in fact, that when I forged a knife out in the desert about a month and a half ago, I forgot to temper it, and when we chopped through the lamb shank with it, it was a weird party. We chipped the edge of the blade. But tempering, you'll bring that back out. So you reheat after you've done your heat treatment, and you can remove some of that hardness, which makes it brittle, and wind up with a more flexible blade. The Japanese were fantastic with this. You've got 2 different kinds of steel, and it's differentially heat treated, so you've got a really, really flexible spine with a ridiculously hard, sharp edge, and it's sort of like the ultimate cutting tool without ever melting the steel. They just forge welded multiple chunks together until they finally got a refined product. We're going to be melting, so it's a lot easier. The other thing is plastic deformation. So I use a hammer a lot. You can beat steel, you can bend it, and you can roll it out. These are all the same sort of process, and they're almost interchangeable. If I have a rolling mill, I can do the same things that I can do with a free hammer or a fly press or a power hammer. Then we've got shearing operations. This is where things get a little bit complex. Regardless of how you look at it, whether it's a mill, a drill, a bandsaw, or actually a set of shears for a piece of sheet metal, it's all the same operation where we're removing a chip of material from a parent stock. This is highly reductionist, but it actually works because those are also interchangeable. I'll have a little bit more waste if I use an end mill to cut through a piece of sheet metal, but I'm still doing the same operation, and I'll get a clean cut and it'll be accurate. So when we need to consolidate things for, again, that launch mass, we can start looking at these as similar enough to where we